Alrighty then, this is my second new Arduino project. Got a transistorized, I think, temperature sensor hooked up to the Arduino. So it's got positive rail going to the first leg. You can see that. Okay, so the first leg to the left is going from the positive rail. The last leg on the right goes to the negative rail, and the middle rail gets fed into A0, analog input 0. So that gives me a value from 1 to 1024, and I'll show you the code in a little bit where I do the conversion to from value back to voltage, and then from voltage to Celsius, from Celsius to Fahrenheit, since I'm living in a Fahrenheit country. And here is the binary output. So right now it is fluctuating between, focus, 75 and 76. A little warm in here. If I hold the sensor right like that, it'll start jumping. Oop. There's 85. And then when it's too high a value, the LEDs will blink up. If the value is too low, if it's colder than 70 degrees, the LEDs will blink downwards. So now the sensor is cooling back off to room temperature. And I've got power in from the USB to a standard Apple charger. I'll order a nice battery plug for a 9-volt battery later to go to there. So that's it for the hardware. I'll show you the code now. I'll just give you a quick brush through first of all, and then if you're still with me and you're still interested, I'll tell you in detail what it does. So my sensor is plugged into analog 0, as I said before, and then my LEDs are pin 2 through 5 digital pin. Then I go through and most of this code is from the Arduino starter kit. It actually came from the project called the Loveometer, and I adapted it to just a general purpose thermometer with binary output, so I just call it the thermometer. So here it just initializes the LED pins as analog output, or sorry, digital output, and sets them to low, so the lights are all off to begin with. Just to make things more sensible, I put a lot of the math stuff into functions. So this function just converts the ADC values from 0 to 1023 into volts. And then from volts, we convert to Celsius. And then I convert from Celsius to Fahrenheit because, well, I'm in the US. Sorry. And then I have a couple other functions that blink the LEDs like I showed you just a second ago. When the temperature is above what the 4-bit output, the 4 LEDs can display, it blinks the LEDs in an upward sequence. And when the temperature is too low for the LEDs to display or to represent, it blinks downwards in a sequence. That's basically they're the same basic function, except one's going up, one's going down. Another function for the purpose of abstraction, I wanted to have a function that would be really easy for me to say, okay, LED 1 through 4, here's their states. Pass off all the digital rights to a function to put all those statements into one line, make it really neat. So that's what that function does. So here's our main loop. We're going to read the sensor value, and then skipping some of the stuff that doesn't make sense just yet. We want to do we're calling val to volts to convert it to voltage, and then volts to Celsius to give us the Celsius temperature. Then Celsius to Fahrenheit, and then I set my base temperature at 70. So I take the difference from the Fahrenheit temperature and 70, set that to temp diff, and that is the number I use to represent on the binary display the 4 LEDs. So all 4 LEDs off means 70 degrees, all 4 LEDs on means 85 degrees. That's the range I can display, which is pretty good for room temperature. It's pretty uncomfortable if it's below 70, well, for most people anyway, and it's pretty uncomfortable for just about everybody to be above 85. That's really hot for the inside of a room, even in Texas. So if the temperature difference is less than 0, aka the temperature is less than 70, blink the LEDs downwards 2 times. If it's above 15, or in other words, above 85 degrees, blink them up. These are the variables that were used to define the LED states. I'll talk to you about those a little bit more later. And so I wanted to have some sensible way of converting, the decimal value into binary, but I didn't want to be really heavy on the math. So here is what I worked out, and I made a Perl script just to test out the math, and it worked. So basically, if this value is above 8, then subtract 8 from the value and set that the LED that represents the number 8, which is the most significant number, high. Same value for 4, same value for 2, same function for 1. So basically this is 2 to the 0th power, 2 to the 1st power, let me get it, 2 to the 2nd power, and 2 to the 3rd power. That's what the LEDs represent, because they're binary. They represent the binary number equivalent of the temperature differences. And then one nice neat call to set LEDs sets all those states. Go on and then have a 1-second delay. And someday I'm going to figure out how to do that more power efficiently. If you Google for, Arduino save battery, you'll find a really exhaustive article on how to trigger some of the pico power functions in the @mega, whatever it is. I'm sorry, it's 9:30. I forgot what the processor number is, but whatever comes on the Arduino Uno. So that's it for the basic run through the code. I'm going to go back up to the top and give you the gory details. This is pretty obvious, these guys up here. So, let's go up here. Define serial on. So what does that do? That is a C preprocessor statement, and it's saying define something akin to a constant variable, but it's not being stored in the Arduino at all. It's not in the object code at all. It is basically something that's defined by the compiler for the compiler at compile time only. So we'll go on from there. And here's another one. And I'll talk about what aref low means in a little bit. So serial on is basically a flag I have to say I want serial output. So go down here, if def serial on. Now see, it doesn't look like a normal statement you see in code for the Arduino or in C if you're familiar with C. It's got the hash sign in front of it, which you might be familiar with if you're familiar with C. So what that's telling is that is a directive to the compiler. It's not going to be translated into code, but it's going to make decisions about the code that the compiler creates. So if serial on is defined, then we're gonna do serial begin. The reason I do it like this instead of a variable, just as a bit of a perfectionist I am, doing it this way means that if I don't have it on, which I do not have it on up here, it will not even link to the libraries or the code that's required to run the serial. It basically cuts the executable size in half. If I have serial on, it's about a 5K executable that gets uploaded to the Arduino. Without it, it's about a 2K or 2.5K executable. I know I'm being a perfectionist, but that's what I love about microcontroller programming. It forces you to not be just a complete sloppy pig and string together enormous libraries and objects if you don't absolutely have to. So going on from there, so basically all the statements for serial on, I'll just address real quick. If I go down all the way down here, it's basically that's my debug, and there's no point in having it on if I'm not going to use it. And it's easy enough to recompile the thing, uncomment it, recompile it, and upload it to the Arduino to be able to get my serial stuff. So when it's on, it gives me, I don't have it hooked up right now so I can't show you, but it gives me sensor value, current calculated voltage, calculated degrees Celsius, degrees Fahrenheit, and the temperature difference, which I put in there for debugging. And was there anything else for serial? Nope, not anymore. Wait, what about that? Oh, print line. You got to end your line, it helps. So, arefflow. Problem I had with this fun little project is I implemented a fractional LED. I had a green LED at the top of the other three, actually it was at the time. I only had 3 bits of display at the time. And I was like, isn't this going to be great? I can hook up the green LED to a PWM pin, and I can get a fractional reading of my temperature. I can see the temperature smoothly changing and varying. But it didn't work. It just kind of jumped around just as much as the other lights did, and I couldn't figure out why until I, turned on the serial debugging and had a look. And the numbers were jumping whole numbers. And the problem is this, with the temperature sensor I'm using, I forget exactly the math, but okay, so the range, the theoretical range of the sensor, if it went all the way from 0 to 5 volts, that would correspond to, and I'll show you the math down here. Let's see. So yeah, so basically this is just translating the value to the voltage, but the voltage, so each volt becomes 100 degrees Celsius. So the theoretical range of the sensor is from minus 50 Celsius to 450 Celsius. Of course, it'll melt down to slag by the time you reach 200. So the problem I had is with a 10-bit ADC that the Arduino has, which is the 0 to 1024 values possible, there's just not enough resolution for me to get a fractional temperature out of the thing. So what I did some research on was what's called analog reference. And what you can do is set the analog reference of the analog inputs to different values. You can either feed an actual voltage to the AREF pin on the Arduino, or you can set it to a different value depending on what kind of microcontroller it's got. So with the Arduino Uno, the only option I had was to switch it to a 1.1 volt analog reference, and that's what the internal means. It's 1.1 volts instead of 5 volts. So suddenly that 10-bit resolution range isn't spread across humongously high voltages that it will never reach in ordinary life, but it's all compressed down to a reasonable range for the sensor. So for 1.1 volts, that's a range of 110 degrees Celsius. So that means that it would be a range possible from minus 50 to 60 degrees Celsius. So theoretically, if you were in a place that was hot enough to be 60 degrees Celsius, you'd probably have more problems than just the sensor. But since theoretically it could do something bad to the Arduino, I have it turned off. The main reason I turned it off is it really didn't help with the resolution that much. I mean, it helped with the resolution, but did not help with the accuracy of the fine detail of the temperature that I was reading. I don't know if it's the Arduino or the sensor itself. It wasn't possible to get fractional Fahrenheit, really good fractional Fahrenheit readings and see the actual temperature fluctuations. At least it didn't seem to me in the testing I did. So I leave arefflow off, so it's using the normal 5 volt analog reference. And I think that's about it. I don't think there's anything else I need to explain with this code. And I'll see if I can post the code somewhere. just if anybody's really curious. I do love a little bit of programming, so